So sequence and series are going to be our last topic. So let's jump in and just see what we're doing. Okay, we want to find the first 5 terms of a sequence, and we'll talk about what that means. And the series, again, we'll talk about that, given by this. Now, what is this? Okay, let's talk about what this thing here is. This is just notation. Okay, and what we have is the following. This is, let's say, an exponential function here. And what I'm saying is the domain here is the set of all real numbers. So x here has to come from the set of all real numbers. So if I change it so that the domain is the natural numbers, n for natural numbers, and the natural numbers are 1, 2, 3, 4, 5, 6, whatever, the counting numbers. Okay, so we use n for natural numbers. Well, then instead of using the f, for some reason, we use A, B, C, those kinds of things. Whatever, it's just what we do. So, okay, so instead of calling it AN, the rule, the whole function, I'm just going to give you the rule. And the assumption is, unless I say otherwise, it's the set of natural numbers, 1, 2, 3, so forth and so on. That's the idea. And then to even make it shorter, we don't write A of n, we just write AN. I don't know, that's what it is. Okay, so that's the idea. Okay, so that's where this notation comes from. When I write this AN, I mean this function here. Okay, so that's all that means. And all I want to do is calculate, well, the first 5 values here. Right, that's what the sequence is, the first 5 values. So just make a table, n is the variable, and I want 5 terms. So unless they say otherwise, it starts at 1. So 1 to 5, and we just calculate the value of the function. Remember, this is like saying f of n. This is an. So when n is 1, just plug n equals 1 in here, and you get 2 to the first power. 2. When n is 2, you just plug in and you get 2 squared, 4. And so forth and so on. I mean, it's pretty straightforward. All you can do is basically change the function, right? That's it. And maybe not start at 1, start at 2, start at -1. That's the sequence. So what's the series? Well, the series is the sum. The series is the sum. So just sum them up. We're going to go sum up the 5 terms, right? 5 terms starting at 1. So the first S1 is A1, 2. And then is 2s2. Sum up the first 2 terms. See, I'm going to get 2 and 4. 2 plus 4, 6. The third, s3. Well, the first 3 terms, a1 plus a2 plus a3. Just sum them up. See over here. Sum them up. 14. When n is 4, sum up the first 4 terms. 30 and 62. And that's it. That's all they asked. That's what they asked. And that's it. I mean, you just need to make a table. This is the kind of thing that Excel does well. You could just do this on a spreadsheet. Okay? Now, there's a shorthand way to do this. Here's the problem. Now, just calm down. Just calm down. Get all stressed. People get stressed out about this. I understand, but let's just analyze what this is. That there is a sigma. Sigma is Greek for S. And S stands for sum. So the notation says sum these things up. Well, that's pretty good. Okay, what? Here's our function. Here's our function. They just put it right there. That's our function. And they say start at the bottom when n is 1 and go to the top when n is 5. I mean, it's really pretty clever. I mean, it's not bad, but I mean, it's as far as these things go. So, I mean, this notation is fine. Sum the function 2n, start at the bottom at 1 and go to the top at 5. We just did this. This is exactly the last one. So this is just a shorthand way of getting you to do what we did in the last example. So this is how you usually see it, because you have to do the sequence and the series here. Right? So that's it. So it's 62. The sum is that's asking us for sum from 1 to 5, so that's S5. That's 62. And that's it. I mean, that's great. Now, I just put this one in because it has a different variable k just to throw you off. And notice I'm starting at -1. But okay, big deal. Start at -1, the variable is a k, go to the top 3. Okay, so notice here, k is my variable. I start at -1, and I go all the way up to 3. Okay, and you just figure it out. My function is k squared, so ak is k squared. Just put it in, sum them up. So they want the sum. So when k is -1, just substitute -1 in for k. -1 times -1 is 1. The sum is 1. When k is 0, 0 times 0 is 0. Sum these first two up, 1. When k is 1, okay, 1 times 1 is 1. Sum them up, 2. When k is 2, 2 times 2 is 4. Sum them up, 6. When k is 3, 3 times 3 is 9. Sum them up, 15. And so that's it. I mean, that's about all that can happen. I mean, people can change the rule or make you start or end at different places, but that's pretty much all you can do with that. Okay, so that's pretty much all you can say. You can sum things up to any finite number. Spreadsheets are great for this and so forth. Now, if we specialize the type of sequence we're talking about, then we can say more. And geometric are probably the most famous. So what I'm saying is the ratio, R stands for ratio, of two terms is a constant. It's fixed. So I'm saying compare A2 to A1. Notice it's 2 to 1. And that's a constant, R. 3 to 2, that's a constant, R. 4 to 3, that's the constant, R. Okay, you get it, right? You get the pattern here. Okay, here's a sequence. And we want to show that it's geometric. Show that the sequence is geometric. Now look, they've even made it simple for you. They just give you the values here. So they're telling you that right now that when n is 1, A1 is 1. When n is 2, A2 is 1/2. Okay, now we have when n is 3, A3 is 1/4, and so on and so on. So they just give you the values. You don't even have to calculate it with a formula, right? They just flat out tell you. Is it geometric? Is there an R? Well, look at the terms. A2 to A1. Now it's 2 to 1. R is A2. A2 is 1/2. A1 is 1. So the ratio is 1/2. Check the next one. 3 to 2. So it's 1/4 divided by 1/2 is 1/2. Check the next one. A3 to A2. No, then this was a typo, right? This should be A4 to A3 here. A4 to A3. You see it's 1/8 to 1/4, but it's still 1/2. Typo there. So the ratio is 1/2. So it is. So it's a geometric series. Okay, it's a geometric series. So what can we do with a geometric series? And this is why they were a big deal, because I think they were the first ones where you could show this is true. Now let's just look at this. First of all, we're saying this is a symbol infinite. So we're summing from 1 to forever. You just keep adding on. And that's the thing with this. You're summing forever. And they're not zeros. You're not summing zeros or plus and minus, 1 plus or minus. You're summing forever. And it equals a number, a finite number. And this was the big deal, because it could mean you could sum things up forever and ever and get a number, a finite outcome. Now notice, it's only true as long as the ratio, absolute value of the ratio, is less than 1. Now people apply this by accident to other things, but it only works if it's less than 1. If the ratio equals 1 or is greater than 1, this result, I don't know. All this says is if the ratio, absolute value, is less than 1, I guarantee this result. Okay? So be careful. People really abuse this. They'll plug it in when the R is 2 and they'll say, I don't know why it didn't work. Okay, determine the sum of the series given by. So again, this is a series. Series are when you add things up. Remember, series are when you add things up. Sequence is when you just list the values. So how do you do it? Well, you have to know what the terms are. See, the first term is A1 is 1. That's the second term. A2 is 1/2. A3 is 1/4. A4 is 1/8. And we already checked in the previous example that the ratio is 1/2. right? So we're good to go. Now we notice the absolute value of 1/2 is still 1/2. So we have that. We meet the criteria. Okay, let me move that over. So this sum equals the first term divided by 1 minus r. Such a simple formula too. Here's our sum. Here's our terms. Let's just move them down here, right? Just move it down here. So the sum equals this. So we have this, right? So all I have to do is put my a1, my first term, here. Now, in this case, it's 1. The formula isn't 1 over 1 minus r. It just so happens my first term is 1. Next, I want to plug my ratio in here and do it. It just equals 2. Very simple. It equals 2. And that's remarkable. Remarkable. You summed up infinitely many terms, and it equals 2. Infinitely many. Now, admittedly, look, they get smaller. They get smaller. But you're still summing up infinitely many terms. And it comes up not even a big number, 2. It's just 2. So that's the idea here. That's a big deal. So what you should be able to do after this section is you can sum any finite sum. Any sequence I give you, you should be able to sum it up to 5 terms, 10 terms. In principle, any finite, million, but okay, for a test, 5. Right, sum up the terms, do the sequence in the series. Okay, the sum is the series. Right, but it's a finite number of terms, right? It's just a finite number of terms. Find the sum of the geometric series. Now this is going to sum out to infinity, right? This is going to go out usually because, I mean, the finite terms you can just do it the regular way. But this is going to be one of those probably sum to infinity, okay? So you just use the formula for that. Okay, so to compute the sum. And that's it, okay guys? So that's it. That concludes the class. That's the last of our topics. So good luck with that, and good luck with things in general.